Hello, AP Chemistry, and now we're going to talk about being away from standard conditions. So if we look here, right, not means standard. So this is my standard delta G value, which we can calculate using standard energies of formation, right? Or we can use it calculating delta G equals delta H minus T delta S, where all terms are at standard conditions, okay? And this is non-standard, right? So all we're doing here is we're saying this is standard conditions, and then we're adding a correction factor. Okay, standard conditions plus our correction factor, all right, gives me my delta G away from standard conditions. Okay, so it's like a baseline, we apply a correction, and then we get our actual value. Okay, now, if we are at equilibrium, thinking back to what we talked to before, we're at equilibrium, delta G happens to equal 0, we get the equation that says delta G is equal to negative RT ln Q, yes? Where in this case, though, if we're at equilibrium, Q is replaced with a K, which right now sounds like nonsense because you're like, I don't know what either of those mean, but we will momentarily, okay? So this is our special condition which applies at equilibrium because we know that delta G equals 0, meaning that neither the forward nor the reverse reactions are occurring, okay? Just so happens, by the way, that this is our equilibrium constant. It is the term that defines where equilibrium happens for any given reaction, where again, equilibrium is where macroscopically no further change is observed, and microscopically the concentrations of all species have stopped changing, okay? Which is why macroscopically we no longer observe any change, okay? And R is the same constant, is the universal gas constant expressed in different units. This is 8.314 joules per mole Kelvin, okay? T is our temperature in Kelvin, and K is our equilibrium constant, okay? And delta G is the same delta G. So what this means is that this gives us a way to sort of compare delta G to where equilibrium is for our particular reaction, okay? Now, let's take a moment and talk about what equilibrium is. Okay, so K, we already described as our equilibrium constant. And our equilibrium constant is based on the law of mass action. Okay, the law of mass action is a way that we can tie all these things together using our coefficients, where K is equal to products raised to their coefficients over reactants raised to their coefficients. Okay, so we have products raised to their coefficients over reactants raised to their coefficients, where this information in here in square brackets will always indicate concentration. Okay, square brackets, these are our concentrations. So the concentration of CD over AB raised to their respective coefficients. So what this kind of means, right, is that it's kind of like saying we have the concentration of product over the concentration of reactant, which means that, right, if we have a lot more product than reactant, then my K value is going to be what? Greater than 1, yes? Now, if we had the alternate situation where my product was less than my reactant, I'm going to have a K value that is, ding, 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 less than 1. Yes? Does that make sense? Just based on the concept of fractions, yeah? So if my product is likely to be greater than my reactant, then my K is greater than 1, right? And then otherwise we have this situation, right? So again, right, equilibrium is where my reaction actually comes to rest, okay? We talk about how we have limiting reactants and excess reactants, and for a lot of really standard reactions, that is the case. A lot of reactions are governed differently, right? Where they have a natural place where based on the amount of each thing present that they will come to rest, okay? For now, suffice it to say that if our process ends with a lot more product than reactant, we have K is greater than 1. If it ends with less product than reactant, we get a K is less than 1. Q, right, is sort of like an instantaneous snapshot of a reaction. Instantaneous. I'm missing some letters there. Lots of letters. Where does it say instant? Instant snapshot of our process, wherein K means our concentrations at equilibrium, Q means our concentrations at any given point in time, right? And they're really the same basic thing, okay? Whereas we're not going to talk about Q very much now, but we will spend multiple chapters talking about it later. And we've already defined what equilibrium is, okay? So then, if we go back to this equation here, right, what this says is if my equilibrium constant favors the formation of product, courtesy of this negative sign and this ln, right, then I'm going to get a negative delta G. Yes? If my reaction favors the formation of product, meaning K greater than 1, I'm going to get a negative delta G. Okay? Now, if the equilibrium constant for my reaction favors the formation of reactant, meaning my K is less than 1, natural log of that, with a negative sign attached, means I'm going to get a positive delta G. Okay? One more time. From the other point of view, if I have a negative delta G, meaning a thermodynamically favorable process, I'm going to end up with a K value greater than 1, which means my reaction favors the formation of product. If I have a delta G value that is negative, I'm going to end up with a K value that is less than 1, saying my reaction favors the formation of reactant. Okay? And note that that's just one of the natural log properties with the negative out front. Yes? Your book also has the alternate way with the E versus the natural log. This is how I prefer it, but you can go look at that one if you prefer the E in it. Okay. And that's just the rearranging of this, yeah? If we solve it with raised to the E, whatever floats your boat. Okay, now, let's go ahead and look at this diagram. This is one of the figures from your textbook, and this is the Born-Haber process, which we'll talk about more in a next chapter. But so we have our nitrogen plus hydrogen to give ammonia. Don't forget, you're supposed to know this formula, and you're supposed to know what it's called. So here, right, free energy, so this is our delta G, okay? And so what this says, right, is that if we have all N2 and H3, right, we are spontaneous. We will spontaneously go forward, right, and make product. If instead we only had ammonia in our bucket, right, we will go in this direction, right? And so there is an interplay here where this is where equilibrium happens, where there is a mixture of things such that my delta G is equal to 0, right, and we've reached equilibrium, which again, we will work with a lot more extensively in a couple of chapters. But for now, like I said, suffice it to say it's the relationship of the amount of product relative to the amount of reactant at equilibrium, the place where macroscopically no more change is observed because microscopically the amounts of the reactants and the product's concentrations are constant. All right. Thank you for listening. Be good, and I will see you soon. Bye.